So Nil has given a sort of overview of probabilistic programming with some specific examples, which is interesting. And Church, which was Noah Goodman's sort of probabilistic version of Scheme, as he was showing you, that wasn't the first probabilistic programming language, but it was the first popular probabilistic programming language. So that was the language that got the computer science world excited about probabilistic programming. Now, since that time, it's become a favorite PhD thesis topic to create a new probabilistic programming language. So there's been like dozens or maybe hundreds of probabilistic programming languages, most of which have only one programmer who is the inventor of the language, who wrote their thesis on it. And so much that Frank Wood, who gave a tutorial on probabilistic programming at the AGI conference a couple of years ago, he made a public plea, like, please, no one develop any more probabilistic programming languages. Like, it's not that interesting to take a programming language and then add probabilistic instruments to it, because in essence, you could take any programming language and then you could add some primitives for sampling from a distribution, and it's sort of interesting. But the weakness of these things is underneath the hood, what it's doing is just some kind of Monte Carlo random sampling of some variable according to some probability distribution, and that's cool for doing simple examples, but then in the end it's not scalable for large problems. But Alexei Polipov, who visited us here at PolyU, did some interesting work where he was using probabilistic programming to wrap up what he called optimization queries. So what he was doing, instead of having a primitive that would sort of sample from a distribution by Monte Carlo sampling, he would try to find basically the highest probability value according to some distribution. So what he called an optimization query. And then behind the scenes he used a genetic algorithm to try to search and find which value was most probable according to some distribution. And
that sounds like an expectation value. Oh no.
Not expectation.
All right, yes.
It could be. You know? Yeah, it depends on the distribution, right? So for a nice distribution, that would be the value that realized the expectation, right?
Yes. Yeah. Sorry.
Yeah. For a bimodal distribution, it wouldn't have to be. So it depends. Right? But that was interesting, just in that it was different, and the perspective he tried to give me was probabilistic programming as an elegant way to wrap up other algorithms. So he suggested maybe we could develop a probabilistic programming type wrapper for various OpenCog algorithms that would make it simpler to interface with OpenCog algorithms, even though behind the scenes it would be our same old OpenCog AI algorithms. And so I started to think about that, and what I came up with is that in a lot of OpenCog algorithms, in essence, what you're doing behind the scenes is sampling from some distribution, but you don't necessarily need to sample from the entire distribution and get a model of the whole distribution, and nor do you just need the value that is the most probable, but you're trying to do sort of fitness proportionate sampling. So you're trying to sample things from a distribution with a probability proportional to how to the distribution, to how good the thing is. So as in a genetic algorithm where you have a fitness function and you're trying to grab genotypes with a probability proportional to their fitness. And when I thought about it, it seemed like a lot of OpenCog's algorithms could be cast as a sort of simple wrapper around some fitness proportionate sampling from some distribution. And one example of that, which is a very simple example, is in what Ms. Ghana has recently done with attention allocation, where to update the importance of atoms in the atom space, but not the attentional focus, you're grabbing an atom with a probability proportional to its short-term importance. So that's like a fitness proportionate sampling, where the fitness is STI value. And of course, to the extent that some cognitive process just wants to grab an atom with a probability proportional to its importance to reason on or something, again, that's sampling from the atom space. So what you're doing, you're grabbing something, a random atom, and the probability is proportional to STI. And in that case, you don't really need to normalize it into a probability value, although you could do so. Because if you're sampling from a bunch of values by, say, tournament selection, you don't actually need to normalize them. You just grab two things, compare, see which one is bigger, grab another one, compare, see which one is bigger. Now what was more interesting was thinking about the PLN inference control problem as something that you could frame in terms of probabilistic programming. So to highlight the inference control problem, let me bring up a complicated PLN inference here, if I can. So this was a sort of demo of PLN reasoning that Nil and Eddie put together some time ago, and it used this background knowledge. Bob is human, I'm a human, I'm honest, I know Bob. Friends tend to be honest. People who told the truth about something are honest. People who told a joke are funny. Being funny is similar to being amusing. Bob told Joe the truth about the party. Bob told Jim a joke. There's a certain probability of people being acquaintances. So it's sort of simple common sense knowledge. And the idea is you're trying to find a friend who is both amusing and honest. And then you're observing that he told a joke so that he's amusing, and you're observing that he told the truth so that he's honest. And you're putting all those pieces together to say, well, maybe this guy will be an amusing and honest friend. So it's a very trivial kind of inference, like a little kid will carry out in the back of their mind without even thinking about it. But to spell it out in terms of PLN is a huge pain in the ass, which is the nature of logic. So this HTML page goes through all the inferences involved, both at a high level and a low level. So I'm in step one. Okay, if we know people who told the truth about something are honest, and Bob told Joe the truth about the party, that implies Bob is honest, right? And that's extremely simplistic. On the other hand, that's what it looks like as an actual PLN inference. Once you spell out all the nodes and links there, and I mean, really, once you go through it, there's not much there. Like, this is just saying what type the variable is. Evaluation told the truth about X, Y, Z. So it's if X told the truth to Y about Z, then honest applies to X and so forth. So it's just a bunch of formalism around the deduction rule. But on the other hand, the formalism takes a while to go through and creates some complexity for the AI also. So this HTML demo is in GitHub, and you can go through it step by step and see what the inference is, and then expand each one to see what actual nodes and links were done. So I thought this example, I mean, it's easier to go through it carefully on your own if you're curious. So the Amusing Friend demo is in GitHub. You can download the HTML. But in terms of inference control, what's significant about this is it is a conceptually pretty trivial inference, and you can see by expanding each of these, it involves a large number of low-level logical inference steps. Now, some of them are just sort of 1 + 1 = 2 types of things, where you're rearranging link types into other equivalent link types, so there are no truth value changes. You're just changing formalism. Some of them are probabilistic inferences, like a probabilistic deduction or an abduction or something, where you're using Bayes' rule and the truth value is changing. But the challenge of inference control is, how do you find the series of inference steps like that without exploring such a large number of other possible failed inferences that it takes 2 weeks to find that inference. And right now, what we can do with the logic engine, I mean, we can feed knowledge in and just let it forward chain and do inferences and see where it gets. And sometimes it gets somewhere interesting, sometimes it doesn't. We can almost do the backward chainer. It works in some cases, where you give it a question that you want the answer to, or a statement whose truth value you want evaluated, and it will explore various ways to get to that answer or to evaluate the truth value of that statement. But if it needs to find a long chain of inferences like this, it may take a very long time to find that, because there's a lot of possibilities to explore. So then the problem you have of inference control is choosing which logical inference steps to take, right? So you have some conclusion you want to get, and how do you get it? So in this case, suppose you want to know the degree to which Bob is honest, then that's one inference that can lead to Bob is honest, but there's a lot of other ways you could estimate the truth value that Bob is honest. Like how do you know which of those inferences to choose? And in general, that's going to be an unsolvable, undecidable problem. But
as part of your personality, you could learn, for example, that this inference chain worked last time. It seemed to work well. I'm just going to apply that over and over again to these.
So that's our general concept. Is you do a bunch of relatively simple inferences, and then you look at which sequences of inference steps and which premises were successful in those previous inferences that you did, and then you use the knowledge of which sequences of inference rules and which kinds of premises were useful in your previous inferences. You use that knowledge to bias the choice of rules and premises while you're doing inference, and then you're sort of ramping up in complexity. So you do a bunch of easy ones that don't take that long, mine the patterns, use the patterns you mined from the simple inferences to bias your choices in the slightly more complex ones, and then you ramp up the complexity. And this is sort of the most central AI challenge that we have in the OpenCog paradigm as it stands at this moment, I think, because we're relying on the PLN logic engine to do a lot of things. For example, in the discussion we had yesterday on learning implications to our goals, right? If you don't have hard-coded implications of context and procedure implies goal, you need to learn an implication context and procedure implies goal. Now, we could do that using Moses, evolutionary programming in some cases, or we can do it using our PLN logic engine, but then...
Well, I thought this was I thought you were trying to leap to sample, right?
I am
working in PLN.
Yeah.
Sample ones.
It's sort of recursive. It's sort of recursive there, actually. So that, first of all, to mine the patterns in the previous inferences that you've done. So if you've done a bunch of inferences and saved every successful or unsuccessful inference that was explored, just save those in some other inference history atom space, then you could run OpenCog's pattern miner, which still needs some improvement, on that inference history atom space. You can run the pattern miner on that, and then you will learn which patterns, which sequences of inference rules on which types of premises were useful in getting to the conclusion you want and which were not useful, right? So you can get those patterns. Then once you have those patterns, then we can view that as giving, implicitly that gives a probability distribution over inference chains. It says which chains of inferences have a high probability of yielding the result you want, and which chains of inferences have a low probability of yielding the result you want. So in essence then, when the PLN forward or backward chainer is trying to do proof, at each step it has to decide what inference rule do I apply to what premises to try to estimate the truth value of the conclusion I'm exploring, or to try to find an answer to the question I'm looking at. It needs to find an inference rule on a premise, so then you can view that as it's grabbing a potential inference rule and premise from the distribution over inference rules and premises that is implicit in the pattern's mind from previous inferences. So in essence, that's sampling, and it's fitness proportionate sampling, because you don't need to get a good model of the entire distribution over all possible inferences, because having an accurate model of all the really bad inferences is not that important. And you're also not just trying to find the one inference which will be best, because the knowledge that we have doesn't support that. So it can't be just an optimization query. What you need to do is sample to try to find a bunch of inferences that should be reasonably good, and you keep doing that. So that could be formalized as probabilistic programming, but again, most of the work is behind the scenes, right? It's in building that distribution, which is done by pattern mining on the historical record of inference chains. And then the interesting recursion there, which will be the next step, is that the pattern miner itself is fairly crude. So the pattern miner is just looking for repeated patterns in the history of all inferences. But then PLN itself could be used to generalize among the various patterns mined in the inference history. So if you mine common patterns in inference history, then use PLN to generalize from those patterns, which gives you a better idea of the distribution of which inference
How do you use PLN to generalize?
Well, for example,
I've been calling this clustering, so you're always allergic to the term clustering. So.
Clustering would be just one example. So one key way you could generalize is over the premises, right? So in an inference history, you have rules that were chosen and particular premises. So let's say doing deduction about Linus was useful in one context. Doing deduction about nil was useful in a similar context. Doing deduction about rating was useful in a similar context. Pattern miner found that, but Linus is a person, nil is a person, rating is a person. So then using the fact that all those inherit from person, you could deduce doing deduction about a person was useful in that context, right? And
it requires you to know in advance that they were all persons.
Yeah. But PLN, but they're all atoms, and they may inherit from person, right? So then that's a PLN and inference step. Because the pattern miner is really
a bootstrapping problem where I don't know that they're persons yet. That knowledge is not going to be able.
Yeah, then you can't mine that pattern, right?
But for me, that's where I use the word clustering. I say, here are these three things, so let me group them into one. So it's the thing that's in common.
Yeah.
And I'll give it some arbitrary label, which just happens to in real life correspond.
That could also be useful, but I think for knowing that these guys are people, it's sort of fair to assume the system would know. But if we wanted to know that they were all AI researchers, then the system might not know that, and you might have to form a category of AI researchers, and then PLN could use the inheritance to that cluster of AI researcher, right?
Well, for me, it's language learning, right? I've just got a bunch of words, and the fact that some of them are nouns, I don't know in advance that fact. I I just observe that they tend to be used in the same way. And so I'm just going to say, oh, well, these must be the same because they keep showing up being used in the same way.
I mean, I think both cases exist, right? I mean, there are cases where you know a category that some concepts belong to, and there are cases where you have to form that category by clustering.
Okay.
But even if, let's say we form that category by clustering, then, so we form the category of AI geeks by clustering, so then we know Linus inherits from AI geek, Nil does, and Reiting does, then that inheritance link could be used in PLN and combined with the mind pattern, right? So you need, so that's also interesting. The recursion I was highlighting is if you're using PLN, perhaps along with clustering or other tools, to extend the patterns mined by the pattern miner in the inference history outer space, then PLN being used there will also use sampling from the distribution for its inference control. So you have a case where PLN, to figure out what steps to take, uses sampling from the inference history distribution, but that distribution can be beefed up by PLN using sampling and so forth. So you have hopefully a virtuous cycle there. And this is sort of, this is what Nil will hopefully spend the next year working on. I mean, it's not, and of course Linus's work in language learning, since language learning and concept learning are sort of the same thing in the OpenCog framework, and conceptually there should be a lot of overlap there. But getting this stuff to work is quite difficult, but is critical, because otherwise
the path ahead is clear, which is what I like.
the path ahead is
It's
clear.
going to take a lot of work.
And if it works, then I think OpenCog will work. If it doesn't work, then we're screwed, because we have a logic engine that can only either prove very simple things or take forever, right? So I mean, we need to get scalable inference to work. Otherwise, the whole symbolic AI aspect is hopeless. And I think this has been the thorn in the side of logic-based AI generally, is there's not a scalable control mechanism.
So do people ever look at these inference traces as a graph structure, and then so you kind of look at the statistics of all your successful graph structures, which I think is what you're talking about.
That is what we plan to do.
And then, but then use something like spectral methods over that. Think of a connection matrix where the probabilities between the elements are this history of their appearance in successful traces, and then do like an eigenvector decomposition to say, all right, here's the most successful cut in this, and let's try that first, and kind of cruise down the distribution that way.
I am not aware of work of that nature.
Bing.
No. But that does tie in sort of closely with what
Well, it
we're
kind of
describing.
tries to unify a little bit like the methods that people use in statistical patterns.
So there are interesting papers in the last year from a group at Google on deep neural nets for theorem proving, and that's the closest thing I can think of to that.
Yeah.
So what they did there, they basically take a corpus of proofs out of Mizar, which is this corpus of like a huge amount of mathematics up to the PhD level, formalized in an exact logical language. I'm about these crazy Polish people over generations of grad students. So they took this Mizar corpus of mathematical proofs, and they basically trained a deep neural network on the proofs to recognize what's a valid proofs. Then they have the deep neural net generate new proofs, and they could regenerate like 60% of the proofs in their training database from the deep neural net trained on proofs, which is interesting. The thing is, their neural net doesn't really understand math, like it doesn't understand the semantics of the proofs. It's just looking at statistical patterns of like this Mizar primitive follows that Mizar primitive follows that Mizar primitive. And they still got interesting non-trivial results just from pure statistical co-occurrences among proof sets, because the Mizar proof corpus is quite large, right? Now, my own intuition is that approach is ultimately not what you want. But it's sort of similar to statistical NLP, right? Where you're just looking at word co-occurrences. And I think that won't go as far in math as it does in natural language processing. But it's interesting. And that's not exactly what you're saying, but it's a bit similar, right? They're using a deep neural net to capture those dependencies instead of traditional statistical methods. Right? But the Mizar corpus is interesting for that kind of thing, because that is a corpus of logical derivations that already exists. I guess part of my hope here is that the probabilistic nature of the inferences themselves in some ways makes the problem easier, because you don't have to get it exactly right. Whereas in CRISP, they're improving in mathematics. There's the search space is different without Bayes' rule and other probabilistic heuristics. And I don't think anyone has tried this in a probabilistic logic context, just because that's been much less explored. Like in probabilistic logic, either people are doing Markov logic nets or something, which is very simplified logic, or they're doing very small toy examples with more sophisticated probabilistic logics. And PLN appears to be the only reasonably scalable probabilistic logic that has like fully featured logic with quantifiers and variables without a lot of restrictions and probability values. Well, yeah, there's a lot of... Once you have a corpus of a lot of inference trails saved up in the Postgres, I mean, then there's a lot of different approaches you could take to mining that corpus to try to learn which inference patterns are good.
I think it's a good direction.
And the pattern miner and PLN on it is one way, but you could try the deep learning network on that atom space too and see what you get. Yeah.
What do you think?
So yeah, there's a lot of interesting things to do. So then in that case, I mean, the formalism of defining something like a sample link, where you're saying, I want to sample from some Yeah, the formalism I was looking at may be rearranged when it gets implemented, but the idea was we're sampling from this distribution subject to this constraint, and one could arrange it separately, but one could put the distribution and constraint together. It really doesn't matter. But my observation was that there was often a distribution that would be commonly used together with many additional constraints. But what I did in this wiki page called Open Coggy Probabilistic Programming, which I won't go through now because we've used a lot of time, but I went through and sort of spelled out how you would implement something like Moses or genetic algorithm, how you would represent forward chaining inference or backward chaining inference, or fuzzy matching, or surreal, or clustering. I sort of went through and tried to sketch out how you would represent these different OpenCog algorithms in terms of fitness proportionate sampling from some distribution over the atom space. And the exact ways I did it here, I'm sure, are not the way we would actually do it, but I sketched out enough to convince myself that if you wanted to, you could rewrite most OpenCog algorithms in terms of fitness proportionate sampling from some distribution over the atom space, and the result would be that the code for each algorithm would be much smaller. So there were some papers like this a year or two ago in computer vision, where they were like, using probabilistic programming, we wrote like 30 lines of code that could recognize faces or something. And of course they did, but there was other code behind the scenes that built a distribution over faces using a bunch of machine vision. And then the code to recognize faces was very short by conditioning on that distribution. And I think we could take that same approach in an OpenCog context where, Moses and PLN chaining and clustering, these things are fairly short code because ultimately what they're doing is sampling from distributions that were built with a fair amount of work. And I mean, whether that's worthwhile or not is a matter of taste, but I think in terms of making OpenCog easy to use, this will be one way to make it easier to code new AI algorithms against OpenCog. I mean, that's a different problem than like authoring content for OpenCog easily, or than connecting OpenCog to other IT systems easily. This is more for a researcher who wanted to develop some new algorithm in OpenCog. If you had a variety of ways to build distributions over the atom space, that would make it easier to build algorithms that do different things with those distributions.
Interesting things to do.
Yeah, exactly. Right. So, yeah, I think that is that topic. More comments?
Have you thought about the ways to enable transfer learning within this big distribution that the sample link encompasses?
How would you do?
Like for instance, you learn how to sample well, for instance, to find good candidates for some problem when using Moses, and you want to use this knowledge to learn how to say to do inference control with PLN, or I mean maybe, or say you have do transfer learning across layers of abstraction. Like for instance, you know how to sample, you know how to sample to solve a problem which is rather close to the perceptual data, and you try to use that to solve a more abstract problem. I mean, yeah.
I don't know. What are your thoughts about that? How does it help?
I mean,
PLN abduction should be able to help with transfer learning, but that's PLN, right? Because that's.
Yeah, I mean, I suppose that you might be able to, again, to use the sample link itself or the pattern miner first to try to find.
That's a matter of what is the distribution underlying the sample link, right? And what level of abstraction are the patterns that you mind? I mean, suppose you learned what method is polite to greet people in China, and then you go to Japan, right? And you want to learn how to politely greet people in Japan. So that's a little bit of transfer, right? Now, I mean, you could, you could choose random ways of greeting people, and I guess somehow or other you're better to choose a random way of greeting people from China than from Congo or something, right? Well, PLN abduction should do that for you. Well, I guess you could view that as sampling from a biased distribution, which is conditioned by association with your current situation or something, right? Like if you have a distribution and then you sort of conjunct it with knowledge of your current situation, then
Yep.
you're sampling with a bias distribution, which is like bias to
Yes.
similarity to Japan somehow, right?
Yeah.
So that then you'd be more likely to grab the Chinese greeting than to grab the Congolese greeting because you bias the distribution by similarity to your current context. So there might be some way to look at it like that.
Yeah, and I think the interesting, the interesting thing to explore would be like what kind of abstraction do you use to compare the context? Like, because you could say, okay, China is close to Japan, but
Well, that's intentional similarity, right?
yeah. But you have so many ways to look at, well, how similar, well, depending on the features that you consider. And depending on, how abstract the features are, I see that the potential for doing very wild transfer learning, that is to be, yeah.
I see it. Yeah. Exactly how much is contributed by just intentional inference and PLN abduction versus how much is contributed by biasing the distribution from which you're doing sampling. I'm not sure. There's sort of different ways of doing the same thing, but in essence, that's sort of a different control mechanism. Like biasing the sampling is like doing an abduction after you grab the sample, because it's just Bayes' rule one way or the other.
Yeah.